Welcome to Chapter 29 Light Waves. After you get done with this lecture, you should be able to understand Huygens principle, diffraction, superposition and interference, polarization, and holography. Now, if you throw a rock into a quiet pool, you create a disturbance that spreads outward in concentric rings from the initial disturbance. Huygens proposed that wavefronts of light spreading out from a point source can be regarded as the overlapped crests of tiny secondary waves. Wavefronts are made up of their tinier wavefronts. This idea is called Huygens principle. So here we have a source, a point source, and here we have a wavefront. And this is one wave. Along this wavelength, their wavefront, they're tiny sources, these little dots here, that are sources of secondary wavelets that spread out and together recreate a new wavefront. Now, the new wavefront, in turn, will have set sources that will create a new set of secondary wavelets that will create another wavefront, and that's how light propagates according to Huygens principle. It's just a model, but it's still useful for visualization. Plane waves can be generated in water by successively dipping a horizontally held straight edge into the surface. As the width of the opening, if you send it through a small opening here, as the width of the opening is narrowed, less of the incident wave gets transmitted, but the waves start to spread out in this interesting pattern. And as this opening is narrowed, this pattern becomes more and more pronounced. Now, what's going on here is any wave will diffract or bend around an edge, an obstruction. So you can see here, you can see that there's kind of a little curve here. That's evidence that this light has bent around this edge. As these two edges approach each other, those two effects from the two edges can add. And eventually they get, when this opening width approaches about 1 or 2 times, maybe 3 times the wavelength of the wave, it becomes very pronounced. And this produces diffraction patterns. Diffraction is a bending of waves by means other than reflection and refraction. It's a property of all kinds of waves. And you don't normally see this too much, but if you look at really carefully at shadows, you sometimes can see this. This is a razor blade, and you can see, if you look very carefully, you can see this, it's fuzzy here, and see these dark bands here, these dark lines? That's a diffraction pattern. Now you can make one for yourself. All you need is a hand and a desk lamp. Hold your hand out at arm's length between you and the desk lamp. Preferably an LED light seems to work the best. Hold your fingers very close together, but not quite touching each other. You want to get them as close together as you can get them, and sight through the narrow slit between your two fingers. If you look really carefully, you're going to see a series of dark and light bands, sort of like this. Okay? Now, they won't be shaped like this, but a series of dark and light bands. That's an interference pattern caused by the diffraction of light, and that only occurs because light is a wave. So here's some diffraction patterns. You look really carefully, you can see those dark bands in here. You can see it's kind of fuzzy around the edges. Here, this is actually a penny, and nobody drilled a hole in the penny. This is the diffraction pattern of light around a penny. So what has happened in the center here is the light is actually bent around the edges of the penny and met on the other side on a screen beyond the penny, and met together and made a bright spot in the center. And notice these tiny little rings around here. That's a diffraction pattern. Notice also these here. There's some more of the diffraction pattern. This light is bending around the edges and creating all these different interesting patterns. So light diffract around the edges of a penny and a razor blade interferes, and the interference fringes are formed. And you can see those between your fingers. So waves will diffract after passing through a narrow opening. Here is pictures of waves passing through openings of various sizes. And there's a point at which, when the opening is about 3 or 4 times the wavelength of the wave, you end up with the most effect. So the amount of diffraction depends upon the wavelength of the wave compared to the size of the obstruction and the cast of the shadow. Ideally, you want the obstruction or the opening to be a couple wavelengths big. And light will cast a sharp shadow with some fuzziness at the edges, so the opening is very large compared to the wavelength of light. When the opening is narrow enough to be a few wavelengths of light wide, then you wind up with more diffraction and shadow is fuzzier, and you might start seeing those bands, those narrow bands. Diffraction is a limitation with any optical instrument, including your eyes. When the object's about the same size as the wavelength of light, the diffraction will blur the image. So you end up with this fuzziness around it. So you can't really tell what you're looking at. If the object is smaller than the wavelength of light, you don't get any image at all. So you want to look at really small objects, tiny objects, you can't use regular light. You have to use something which has a very short wavelength. And electron beams have very short wavelengths. And therefore, we have devised something called an electron beam microscope. That uses electric and magnetic fields to focus and magnify images of very tiny objects. When you drive downtown listening to the radio, you may have noticed that you get better reception with a longer wavelength AM band than you do with a shorter wavelength FM band. That's because of the relationship between the size of the AM radio waves, the FM radio waves, with respect to the buildings and the gaps between the buildings. Dolphins will actually use shorter wavelengths when they're trying to catch a fish. They'll switch to a shorter wavelength to get finer detail of what they're trying to catch. And if I remember correctly, bats do that too. Okay, the interference of waves is actually caused by the superposition of waves. Superposition is just a fancy term for addition. So you have two waves, 1 and 2. And if the crest of wave 1 happens to arrive at a certain point at the same time as the crest of wave 2, and the trough of wave 1 happens to arrive at a certain point at the same time as the trough of wave 2, you can kind of tell these are going to add to each other. So the amplitudes are going to add, and you can wind up with a bigger wave. This is called reinforcement, also called constructive interference. On a screen, you will wind up with a bright spot. In the ocean, this can occur in the ocean too, you will wind up with a bigger wave, otherwise maybe known as a rogue wave. So if you ever wondered where that came from, that's possibly it. Okay, now you can also have the situation where the crest of one wave arrives at the same place and time as the trough of the other wave. And similarly, the trough of wave number 1 arrives at the same place and time as the crest of wave number 2. And if these have the same amplitude, you're going to wind up where they completely cancel each other out. That's called destructive interference. And on a screen, you will wind up with a dark spot. And in the ocean, you'd wind up with a smooth spot where there isn't any wave. This is a situation where the crest of this wave doesn't quite match up with the trough or the crest of the other wave. Then you wind up with a partial cancellation. So it's somewhere between, it's not as big as either one of the waves. And then on a screen, you will wind up with a gray area or slightly somewhere between light and dark. On the ocean, you wind up with a smaller wave. This is the interference pattern of overlapping waves from two vibrating sources. Now, if you look very carefully right here, you might see an area where the waves kind of cancel each other out. That's destructive interference. Right next to that is an area where there is constructive interference. Here's destructive, constructive, destructive, constructive, destructive. Now, interference patterns are caused by the interference between a pair of waves. This is an interference pattern. Of course, here we have two waves that are arriving in phase. That is, crest is meeting crest and trough is meeting trough. You wind up with a bright area. That's constructive interference. Here you have crest meeting trough and trough meeting crest, and they wipe each other out. This is destructive interference. You wind up with a dark area. In between these two extremes, you wind up with something in between. Now, constructive interference produces bright regions where the waves reinforce each other. The waves are arriving in phase. So crest is meeting crest and trough is meeting trough. Destructive interference produces dark regions where the waves cancel each other out. The waves are arriving half a wavelength out of phase. So crest meets trough and trough meets crest. This is proof that light is a wave. If you take monochromatic light, that's light of one color, and you shine it on a pair of slits that are just the right spacing and the right size, instead of getting what you would expect, which is just a shadow of this, two of these bright bands surrounded by darkness, you get this interference pattern. And you get a bunch of bands of bright and dark bands here. This is evidence that light is a wave. So here is what this is looked at from the side here. And there's the slits right here. Here's the original light source. Here's the waves passing out to this pattern that shows up on this other screen here. So here's the slits, here's the viewing screen. Okay, so here we have the light from the source, hits the slits, and then fans out from each of these slits. Now, when the two light waves arrive in phase with each other, so crest meets crest and trough meets trough, you wind up with a bright area. That would be the central maximum. You always get that one. Now, above and below the central maximum, you have come to a place where the light will arrive out of phase. So in other words, crest meets trough and trough meets crest. That's due to the difference in length between this path from the upper slit and the path from the lower slit. When that happens, you end up with destructive interference, you end up with the dark band. Same thing down here. If you move further up the screen, eventually you get to the point where the path length difference between the light coming from this slit and the light coming from this slit has to be exactly one wavelength. So they're arriving in phase with each other again, and crest is meeting crest and trough is meeting trough. You wind up with another bright spot here, ditto down here. So that's how this is generated, and it's only because light is a wave and can constructively and destructively interfere with each other to create an interference pattern. Here's the same thing. Here's the two slits showing the waves radiating outward, and of course we have the central maximum surrounded by two dark spots or minimums, surrounded by two more maximums, surrounded by two more minimums. Here's, of course, showing that in a wave tank. And here's what the thing would look like on a screen. Now, the detail on this isn't really good. Here's the central maximum. Here are the two dark areas flanking the central maximum. Then we have two more bright areas. If you look really carefully, you'll see a dark area here and a dark area here. And if you look really carefully, there's a very dim bright here and another very dim bright here. Now, double slits will produce this banding. A single slit, depending upon the size of the slit relative to the wavelength of light, will produce either one bright band like this, or it might produce a single bright one in the middle, flanked by alternating bands of dark and light. I'll show that to you on the next slide. This is a single slit diffraction pattern. It has a central maximum and many smaller, dimmer maximums on either side. And when I had you look between your fingers, this is what you saw. Okay, you may not have realized it because it's not really good experiment, but if you did this with monochromatic light with just the right slit width, you'd end up with this. Now, diffraction grating is like a double slit experiment on steroids. It uses thousands of slits, and it produces a pattern similar to a double slit, only sharper and clearer. And if you shine non-monochromatic light, if you shine white light onto a diffraction grating, you end up with a central white maximum and then these beautiful rainbows that appear on either side. We won't go into detail on this, unfortunately. I wish we had time, but we don't. If you want to learn this, take Physics 122. Now, what is a diffraction grating? It's composed of a large number of close, equally spaced slits for analyzing light sources. Because it can produce a rainbow of color, it can actually be used to measure the wavelengths of light, and it works like a prism to split out the colors of light. The phenomenon of interference occurs for any wave at all. Now, here we have something interesting. We have two thin glass sheets here, separated by an air wedge. And when you shine a single colored or monochromatic light on this, some of the light will bounce off this surface, this interface here, the upper side of the air wedge, and some of it bounces off the lower side of the air wedge. So it bounces off inside the glass here and just at the top of this glass. And depending on the difference here, the length difference here, the path length difference, you will end up with either constructive or destructive interference or something else. And what type of interference it is determines what kind of color you get, what you see. So in this case, this would be destructive interference. You can see crest and trough overlap, and this wipes it out. Now, where does the light go? It doesn't disappear. You neither create nor destroy light energy. Light is energy. It comes out the other side. Now, if you change the angle here or the thickness between the air wedge, that'll change what you see. If you look at this from a different angle, you'll see a different color, or you might not see anything, or you might see the color come back, depending on what you're looking at. If you change the distance between the two glass plates, you will see a different color, or maybe nothing. It's very useful for measuring very small imperfections in lenses. Now, it also shows up in thin film interference. So here we have air, gasoline, and water. So oil on water. You've all noticed this out in the parking lot. Okay, after a rainstorm, you look where the cars have dropped oil, and you see these beautiful little spots of oil with all these different colors. You ever wonder what caused that? Well, here it is. Now, here's how interference colors occur by reflection from thin film. There's a thin film of gasoline that is just the right thickness, and this angle is just exactly right to result in the destructive interference of blue light. That is, of course, the reflected blue light that's coming off the top of this surface here and this surface, top and bottom of the gasoline surface here, is 180 degrees out of phase with each other. So in other words, crest meets trough and trough meets crest, in which case that wipes out the blue light. It's reflected blue light. Where does the light go? It doesn't disappear. It goes through and it's transmitted through the film. So the blue light is subtracted from the incident film, leaving either, if it's white light coming in, you see the complementary color here. If it's blue light coming in, then you're going to see nothing. Now, if the incident light is white, the complementary and reflected color is then yellow, and the transmitted color is still blue. If the incident beam was blue, you would see no reflected light because it's been subtracted out. If you change the thickness of the film or the angle at which you view it, then you're going to see a different set of colors. You'll see a different color that's reflected and a complementary color that goes through, and vice versa. This is responsible for the colors on a soap bubble. Right here, this is indication, these different bands of colors are indication that the soap bubble is of varying thickness. It's not all constant thickness, and you're viewing it at different angles because this is a curved surface. This also shows up in things like hummingbird feathers, some insects, oil on water, gasoline on water. Now, this is white light shining on a bubble. Note that the color in bubble are the subtractive primaries, magentas, yellows, and cyans. Now, don't be too worried about this. We're not really cover this because that's chapter 27. If the thin film of gasoline was a bit thinner, the wavelength to be canceled would be that of shorter than that of blue because it was a thinner film. If the blue light were canceled by the double reflection of sunlight from gasoline on a wet surface, the resulting color would be yellow. Yellow is the complementary color of blue. Adding yellow light to blue would create white, so subtracting blue light by cancellation leaves yellow. Now, for more information on complementary colors, you can look at chapter 27. You are not responsible for chapter 27 on test. You don't have to read it if you don't want to. I just put it here because it's interesting. You are responsible for chapter 29 on test. I do expect you to understand that the destructive interference in thin film can subtract wavelengths of light, creating the beautiful colors of a soap bubble or oil slicks. If you see the color blue reflected in the interference from gasoline on water and you lower your head so a greater angle from the normal result, you're likely to see a color having a wavelength shorter than that of blue. The path through the gasoline would be longer, and a longer wavelength would be then canceled. The result of a long wavelength being canceled is a shorter wave, but the longer wavelength would appear on the other side of the film. Now, normal light, unpolarized light, the vibrations of the electric fields are random. They occur in all directions. And we can represent that by all these double-headed arrows in all different directions. Now, it's a pain in the butt to draw. So what we're going to do is we're going to only draw two of them. We have two double-headed arrows. They're perpendicular to each other and they're the same length. Examples of unpolarized light are around you everywhere. Most desk lamps produce only unpolarized lamp. Candle flames, almost everything around you is unpolarized. There are some things that do produce polarized light. Now, how do you polarize light? Well, the simplest way to do this is to run through a polarizing filter. So here we have unpolarized light coming in, and we can represent that by just drawing this double-headed arrow, equal lengths, perpendicular to each other, and it goes through a special film called a Polaroid or a polarizing filter. And what it does, this film has molecules that are lined up in a certain direction, and it will absorb anything that is not in the right direction, not in the correct direction. So anything that is not aligned with the polarization axis of the first polarizer will be absorbed. So you lose half the light here. Anything that isn't vertically polarized disappears. So it's sort of like having a rope that wiggles in all different directions, and you run it through a picket fence. The wiggles that come out are the only ones that are oriented in the same direction as the slats in the picket fence. Now, if you run that light to a second polarizer, and the second polarizer has its axis also oriented in the same direction as the first polarizer's axis, then it's like running it through a second picket fence, and the light comes through here just fine. So you've lost half of it here, but the rest of it comes out. You still have half coming out. Now, if instead you run it through a first polarizer, say it's vertically oriented, and then you run it through a second polarizer that's horizontally oriented, nothing comes out. So what's going on here is it's unpolarized in the first polarizer. That's like the rope wiggling in all different directions. You run it through the first picket fence, it's vertically polarized. Then you get vertically polarized wiggles coming out, like here. So you've lost half of it right here. Then you run it through the second polarizer. The second polarizer is horizontal or perpendicular to the first one. Nothing comes out at that point. So nothing will come out here. So unpolarized light is divided into two internal beams, polarized at right angles to each other. One beam is absorbed while the other beam is transmitted. So that's what happens when you go through here. So when you go through a polarizer, half the light gets absorbed if it's unpolarized incoming. So here we have an unpolarized light source coming through a polarizing filter. The ones that are only come out are the only ones that have components in the vertical direction. So what comes out of this is half the light comes out, only the stuff that has some sort of vertical component. The horizontal components are all wiped out. So for unpolarized incoming light, an ideal Polaroid passes 50% of the incoming light. If the incoming light is already polarized, the Polaroid will pass an amount of light that depends in a very complicated way on the angle between the polarization of the incoming light and the axis of the Polaroid. That is physics 122. So don't worry about that. Okay, this is sort of an interesting little thought problem here. Here is also a demonstration of polarized light and cross-polarizing. So here we have a lady, she's looking through a pair of Polaroid filters, otherwise known as polarizers. And the first one may be vertically polarized. And here's the incoming light, and you can see she's lost a little bit of light when it comes out of here. Coming out is a little darker than it was going in. And it's coming out vertically polarized. And she's sending it through another filter whose axis is also vertical. So she's lost half of it here, but she still gets the same half coming out. And it comes out vertically polarized. Now she's taken this filter, and instead of it having a vertical, now she's got it horizontally. So here's the original light. She's lost half of it here, but now it is horizontally polarized. Then it goes to the second filter, which is still vertically polarized. And nothing comes out here. Now notice down here. This one is still vertically polarized down here, and about half of it's coming out there. This one is horizontally polarized, and half of it's coming out here. But when it goes through both of them, nothing comes out. Now, interestingly enough, if you still have these two, these are cross-polarized. That's what this is. That means the axes are perpendicular to each other or crossed. If instead you put a third polarizer in between the first two, such that the angle of the third one is not aligned with either the first one or the last one. So in other words, it's not, in this case, it's neither vertical nor horizontal. Some of the light gets through. Now, if you have nothing to do, like that's true at this time of the semester, you can use your knowledge of vectors and vector components to explain how light that can't pass through parapolarites that are crossed will pass some light when a third polarizer is sandwiched between them. Now, I don't want you to send this to me. This is not an assignment or anything else like this. It's just something that you can think about, sort of for fun. So here we have a unpolarized incoming light coming in. We have run it through a polarizing filter. It comes out vertically polarized in this case because it's vertical. And if we run it through a second polarizer that's horizontally oriented, so at right angles to the first one, nothing comes out. If instead we have unpolarized light coming in to a polarizing filter, what comes out of the first filter might be vertically polarized in the same direction as the axis of the first filter. And if we turn the second filter in such a way that is not horizontal, some light will pass. Now, if this happens to be the same orientation as this light, you'll get 50% light out. Half of it, 50% here, and if this is vertical with that one, you'll still get 50 out. If these two are, one is vertical and the other is horizontal, you get nothing. If one is vertical and one is something other than horizontal or vertical, you get something between 0 and 50. And how much you get out depends in a very complicated way. It's a cosine squared function of the angle between these two. And that's a subject for Physics 122. Polarization occurs for waves that are transverse. You cannot polarize a longitudinal wave because polarization depends upon the fact that for a transverse wave, the direction of vibration is perpendicular to the direction of motion. For three-dimensional viewing, it depends primarily on the fact that both eyes give their impressions simultaneously or nearly so, each eye viewing the scene from a slightly different angle. This is old-fashioned three-dimensional TV and 3D movies. They use two projectors, and they have Polaroids. Those are polarizing filters on the projectors. One is aligned vertically, the other is aligned horizontally. In order to see the 3D, you had to look at these through a pair of polarized glasses. And the pair of polarized glasses had to have the same orientation as these projectors did, in which case each eye will see the proper view as with a stereoscopic viewer. These are the old-fashioned, you remember those paper glasses they would give you in some movies so that you could see the three dimensions? You might have noticed that when you drive up to a gas pump, if you wear polarized sunglasses, you might not be able to see the display that tells you how much gas you bought and how many gallons you've pumped until you turn your head. You might have to turn your head in order to see the liquid crystal display. That is, of course, the display that the gas pump uses. Liquid crystal displays depend upon polarization of light to work. And this also works in some old LCD TVs and LCD computer screens. If you try to look at those through polarized sunglasses, it can be very difficult, but it's sort of fun. If you tilt your head sideways or turn the glasses, you might be able to see the screen again. Now, a hologram is a two-dimensional photographic plate illuminated with laser light that allows you to see a faithful reproduction of the scene in 3 dimensions. Each point of the object being photographed reflects light of the entire photographic plate, or to the entire photographic plate, so every part of the plate is exposed with light reflected from every part of the object. It is important that the light used to make a hologram be of single frequency and all parts be exactly in phase. It must be coherent, and of course, laser light is coherent. According to Huygens' principle, every point on a wave behaves as a source of new waves. Diffraction is more pronounced for waves passing through what they call small openings. Small means that the width of the opening or the size of the opening is a couple multiples of the wavelength of light. So in other words, 3 or 4 times the wavelength of light. Diffraction can occur for any wave. For viewing tiny objects in an optical microscope, diffraction is a pain in the you-know-what. A diffraction grating relies on light interference. When light undergoes interference, it can sometimes be either increased in amplitude or decreased in amplitude or canceled completely. So constructive interference, the amplitudes will add. Destructive interference, they cancel. And something in between, they partially cancel. When light undergoes interference, the quantity most affected is the amplitude coming out. Interference can be exhibited by all waves. Which of these is a property of light waves but not sound waves? Well, polarization. Polarization only occurs for transverse waves. You cannot polarize sound because sound is a longitudinal wave. Compared with the individual amplitudes of a pair of waves, the greatest amplitude that can be produced by interference is no greater than their sum. You cannot get out more than what you put in. When light waves that are in phase meet, the result is brighter light. If they were out of phase, the result would be dimmer light or no light. A beam of white light that reflects from a pair of closely spaced surfaces has color because some of the reflected light is subtracted from the beam. When light is canceled by the interference in thin films, the color produced is the complement of the color canceled. Now, iridescent colors are often seen when interference occurs in objects such as seashells. The color always produced is the complement of the color canceled. And if the object is clear, if you go on the other side of the object, you'll see the canceled color on the other side of the object. Polarization can occur when waves of light are aligned. An ideal Polaroid will transmit 50% of non-polarized light. So consider non-polarized light as half aligned in one direction and the other half aligned at right angles to the first direction. An ideal Polaroid transmits 100% of light vibrating in one of these two directions. Split in two, that's 50% of the incident light. An ideal Polaroid, on the other hand, transmits 100% of the polarized light if the light coming in is polarized and the polarization is aligned with the polarizer's polarization axis. Two Polaroids, one atop the other with their axes at right angles to each other, whether ideal or not, will transmit 0% of light, right angles. Those are cross-polarized. Nothing gets through cross-polarides. Because of absorption, consider a non-ideal Polaroid, which transmits 40% of the incident non-polarized light. Two such Polaroids, one atop the other with their axis aligned, will transmit something between 0 and 40%. So an ideal transmits 50%, which means 100% of the incident light aligned with the polarization axis is transmitted. But due to some absorption, a Polaroid transmitting only 40% means only 4/5 of the light aligned with the polarization axis is transmitted. So 4/5 of the 40% or 80% of the 40% that gets through the first one gets through both. So that's 32%. And that's between 0 and 40%. Three-dimensional viewing is best seen by people with 2 eyes. Olive Gray makes best use of the phenomena of diffraction. Thank you.